if you want, you can download them and follow along because I'm going to do some interactive stuff with the VM. So, okay. So quick outline of my talk. I'm going to just basically go through what RoCC can do, what you guys can do to change it, what you guys can get out of it, you know, the C++ emulator, the Verilog, how we can look at waveforms, and then if we want to change things, where should you put them? How do I add new instructions? How does my accelerator fit into the RoC interface? Things like this. Okay, so basically RoCC is a chip generator that allows you to set up different configurations for an SoC, and it includes all the software and tools that you need to run these things. And these configurations are specified through the Chisel parameters that you've heard a little bit about. And most of them can be freely changed. And once you've selected what you generate, you either are going down two routes with a C++ emulator or Verilog generation for FPGA or ASIC backends. So if we go into the RoCC directory, we see a lot of files. And so quick overview of all of the things that are in this repository. So Chisel is the hardware description language used at Berkeley for our RTL. We're going to just first talk about all of the submodules. So we see RoCC is the core and all of the including caches. We also have the uncore, which is this outer memory system, and coherence agent. Another thing is hard float, which is our hard FPUs and FMAs. DRAM Sim2 is something we use for DRAM timing emulation for our simulators. And then FPGA Zinc is a repo that is really useful for putting things on FPGA platforms. And then obviously RISC-V tools is the software tool chain that we use. Just quickly going through all the other stuff in here, we have various source and sim folders, and basically csource is things useful for the C++ emulator, and emulator is the directory that gets built in. fsim is for FPGA Verilog generation. Project is just the Scala SPT stuff, and then source is where your actual Chisel source is, so that's full of Scala files that are Chisel. And then vsource and vsim are Verilog source and Verilog generation for the ASIC backends. And there's one other folder in here, RoC template, which is kind of the thing we're going to use later to do a drop-in RoC accelerator. So the first thing we're going to look at is basically the configuration file for RoCC, the RoCC chip, sorry. And so basically, this is what a set of parameters looks like for RoCC chip. It's quite extensive, and it's kind of divided up with these little comments of different sections. And so you see there's like HDIF parameters, which is setting a lot of different things, and you have memory parameters for your physical virtual address bits and other memory interface widths. We can also go through like all the different cache parameters we have set up. Let's see what else is interesting. And then there's kind of constraints on, or different parameters for the tiles setup. And so you can see we have this build RoC none right now. We'll deal with that. We'll change that later. And all these are just kind of parameters that you can mess with yourself. So if we move forward, yeah, so all of these are different configurations. And at the bottom, if we go to the bottom of the file, we see that there's a couple of kind of default configurations that are set up with certain parameters set already to things that are reasonable defaults. And so this set of knobs, so knobs are one of these things that we call basically tunable parameters that you would expose to a Design Space Explorer tool, because they're things that we think are useful to tune over. And so the large default config at the top has this particular set of knob values, which we think is a reasonable default config. But then if you just wanted to test something smaller, just to see if everything's working, we have this small config, which is also included and has a much more restricted set of things. And so if we wanted to simulate one of these, I guess I should just do it. So if you want to simulate one of these, we're going to go with the C++ emulator. We go into the emulator directory, which is where the build files are for those kind of things. And in order to just run the quick tests with the default config that I was showing before, we just type make run ASM tests, and that's going to load up Chisel and start running through compiling Rocket, and then it's going to start doing the tests after that. So this takes a little bit. I thought this was already. You guys might have had this precompiled. I'm not quite sure, but yeah. So this is what it looks like when Chisel runs. In case you haven't seen this before, it's generating C++ code. Now it's running through the compiler to link together the C++ executable. Shouldn't take too much longer. And then we'll see it fly through all of the assembly tests. Also, I just want to note, there's students that can help you if you guys are running into any problems doing this on your machines. Just raise your hand. I think people would be willing to step in. But so this is what happens. Then it just goes through all the assembly tests, and they all eventually pass. So we'll just skip through then that. And so basically, as you saw in that file before, in addition to just running with the default config, on the command line we can specify, to make that small config that we saw. So this is going to have, much smaller cache parameters. And so this will do the same compiling of Rocket chip, but this time it'll have much smaller cache parameters. And oops, I misspelled that. Smart enough to realize I didn't have a capital O. But yeah, assuming I can type correctly, we should see that this compiles into another C++ executable in a second. Yeah, so there we go. And so it's pretty interesting, and we can test this same one in the same way we could before with make run ASM tests giving the small config. So if we wanted to go through and actually modify the configs ourselves and add a different set of parameters, let's say we want to have a different size cache or whatever, we would go back into the config file, which is upper directory into here, and then in this case we're going to say we just want to do the small config, but instead of having just one way for each of the sets, we'll have two ways. And so that just is this simple 4-line little class, and we have it extending the regular default config so it pulls in everything else that we don't want to change. And then we can make this config too. And just like that, we have a whole nother set of cache sizes in our Rocket chip. So that's just a quick example of how you would change kind of some of the basic parameters in Rocket chip. And so the ability to do that pretty quickly on the fly is really a powerful concept of generators. So in the more abstract sense, if you wanted to add something that was more of like a new parameter, not just changing the current parameters, you would end up also working inside of that file, changing the configuration. And so in that list at the top you saw, you can just, and we can add anything here, and then all of these are visible as parameters inside of the normal Chisel parameter system. All of these names come up as things you can look up. And so if we want to add an accelerator, basically that would probably add a lot of different parameters. And so we kind of think that the way to do that would not be to include a bunch of different parameters in this overall config, but rather to have it defined in its own subfolder. And so I think that's kind of the method that we're going with now. But once we get into actually dealing with the accelerators configuration, I'll talk more about that. So now I want to switch to talking about just ISA extensions and the RoC interface in general, which is our kind of easiest way to get something you want to into RISC-V. And so this diagram comes from chapter 8 in the ISA manual. And basically, we have 4 major opcodes set aside for non-standard extensions, named custom 0 through 3. It's worth noting that custom 2 and 3 are reserved for potential future use in RV128. And so maybe if you limit yourself 1 and 2, 0 and 1, you'll never have any problems, but you can feel free to use 2 and 3 for now. And basically, you see the little encoding at the bottom. The RoC interface has 2 source and 1 destination operand and a 7-bit funct field. And basically, those middle bits, XD, XS1, XS2, are kind of telling you, are we using the source or destination operands for any of this instruction? And you can always fall back to just interpreting this yourself, because along with the RoC IO interface comes this whole instruction that you can decode however you would like if you want to get around any of this typical encoding. Yeah, so since this is already kind of rolled into the whole toolchain and everything, you can use custom 0 through 3 in the assembler and it'll understand it. And so this is probably the easiest way to just get in and put something interesting in RISC-V. And so you just need to implement the RoC IO interface, which I'll pull up on the screen, but the next slide also has something, has it kind of something from Yunsep's talk the other day, where we can see a little bit at a higher level. So yeah, this is the instruction encoding. There's all this stuff located in here. But basically, you see we get the command, which is the instruction, and then the registers, and our response is the data and the RD. We're also supposed to take care of these busy supervisor and interrupt signals, basically to make sure that you can virtualize properly. And the busy is for fences, so if the accelerator is performing memory operations, it's supposed to assert that it's busy so that the rocket knows when to wait on a fence. And then these things we also talked about yesterday. And it's kind of for dealing with getting into the instruction memory and the page table walker if you want to deal with TLB stuff. But we'll kind of skim over that for now because our accelerator is not that complicated. So now we're going to go into our RoC template directory, and we want to check out this version of the branch, which now fills in your folder with the source for a SHA-3 accelerator, which was developed for the 250 class to help teach. And so there's a bunch of things in this directory now. We have a C implementation in here. We have the Chisel implementation in here as well. There's some tests that we can use once we implement it and integrate it. We also have the version of the functional that fits in with the functional simulator Spike, and as well as a config file for integrating with Rocket Chip. Oh, and also, so there's this install symlink script, which instead of just copying all these files around, there's just a simple script that puts all the symlinks in place so that you can build all the tools with the files in this directory. And so obviously, when we want to design an accelerator, the first thing we should do is write a functional simulator so we know what to expect from our RTL that we develop. And so if you look in this directory in the ISA sim, we can see what a sample extension in Spike looks like. And so we implement this RoC type. And basically, since our accelerator is pretty simple, it just takes in a message address and a hash address, and then the length, and computes this little hash. We then we only have one of the custom opcode fields that we use. And so it has this type signature, and basically we're able to decode the instruction. We look at the func type to see what it adheres to. And if it's 0, we have to read in the message in the hash, and if it's 1, then we're reading in the length. And after that, we just go forward and do the hashing. But an important thing to note kind of is that since we are doing a simulator, we have to, when we want to read from the simulated system's memory, we need to use these kind of get MMU and then load instructions in order to make sure we're getting from the right part of memory. But then we can just have, this is just the C implementation of SHA-3, and since it's functional simulator, just all happens at once. And then, yeah, so that's how the spike instrumentation works. So now I guess we've already installed the symlinks, and so we can just go out of here and we can rebuild spike with our new changes. So now we'll link in and have this, our new functional extension, our functional model of the SHA-3 accelerator. And so this shouldn't take too long because it's not too big of a thing, but basically that allows us to use this -- extension equals SHA-3, which we defined in that header file that we looked at. And once this finishes, then we can test that out. So because in order to test it out, we have a few tests in that RoC template directory, these software and the RoC tests. Each of them has a benchmark version, which basically just removes any checking of the results. And the software versions are just using the C implementation and versus the RoC implementations are using inline assembly. So they're already precompiled, but we should quickly look at what it looks like when you're writing to use an accelerator. So because we already have support for these custom 0 opcodes in the assembler, we don't need to touch the bin utils at all, and we can just write this, assuming we know the syntax. We can just write the exact assembly we need, and obviously these could be wrapped inside of a function header if you want, so that you don't need to see assembly in all of your code. But that's kind of the gist of it. I guess it's interesting to note that the operands to this are basically 0 if you don't care about using that register. Otherwise, it's the standard assembly syntax to pull in the addresses of all of the data that we need. And then, so now that we have that, we can basically test in this directory. We can say, let's just test the regular software version first. And we see that that works flawlessly, as you would expect. And if we try to run the RoC version with our non-extended version, we get an error, as you would expect. And so then when we add our -- extension SHA-3, success. Our functional model works and validates that our program's correct. So now we're going to move on to actually making it a Chisel accelerator. And so we don't actually have to go into all the details of how it's implemented because that would take a long time, but quickly looking at, we see we have this little, config at the bottom of our accelerator definition that kind of looks in the same way that the rocket chip configs looked, because it's using Chisel parameters as well. The only difference you'll notice is the set of constraints, which is something that we use in the class to use with the jackhammer tool as a design space exploration thing. So we kind of set what values you can look for in order to give it space. This is a kind of simplistic example with not a lot of interactions, but there is constraints here, and it will figure out which parts of the space are valid. So in order to integrate this with Rocket Chip, we have in the config directory of the rock template thing, we have another config that matches pretty much basically the same thing as before, but this one is symlinked to from the rocket chip directory. And so the result of it extending the rocket ship config is that we can go into the emulator and we can make our accelerated version of rocket chip, which will plop in the build rock slot. It'll give it passes basically a pointer to how do you make a SHA-3 accelerator, and it fits in with the rock IO, so it just plops right in, and we can get the same C++ emulator out. So obviously, once this compiles, we'll run a quick test to make sure that our accelerated version still passes the same software and rock-based SHA-3 tests. You can see that on the side. So if we run the software version with our new emulator, oh, that's, oops. Got to actually point it to the file. So, so this is kind of like a spurious failure because the code is so basically this implementation. So the .h flag that you pass the PK give you stats, and I'm pretty sure this is still succeeding correctly. It's just the failure warning is because of the return code at the end of the C function from before. But we can see that when we switch to using the accelerated version, we get significantly fewer cycles. Yeah, so that's a good sign. So next step is, what do we want to do if we want to get some sort of debugging information out of our tool? So obviously we could just use Chisel support for printf statements where we write out values from during the run, but we also have also has support for emitting VCDs from the emulator. So if we type make debug, we will get an executable that can produce a VCD for any program that it runs. And so in a second, once this finishes compiling, we can run that command. That should run a different benchmark, and will output a VCD that we can open in GTK Wave shortly. So I guess while the things are compiling, we can, where's my mouse? I can just make sure that my VM is still set up correctly. Okay, close this one. So basically, once you have the debug emulator, you pass it the -v flag to tell it where to write the VCD file. And then we're also going to just pass it a straight hex file to run rather than loading something through the proxy kernel, which would take a lot longer and build a much bigger VCD dump. Once this finishes, once compiling debug mode, I think it has a lot more signals going along in C++ emulator, so it takes a little bit more time to compile. But we should be done soon. Well, I'll just open up. So I actually have, well, I want to show you guys how to do it, so it's worth waiting. Equals out slash. Okay, so there we go. That test finishes pretty quickly, and now we have our test.vcd, which we can open in GTK wave, as you would expect. So this shows you that Chisel is not that unreasonable, at least when it comes from the VCD side. You can still see all of signals are slightly mangled, but it's still perfectly hierarchy is maintained, and you can see what's happening in here. If you look into the core, all of these signals, see something that's interesting. But yeah, so all of this obviously is just add some signal. We'll see that, things toggle eventually once the thing starts running. So that's VCD waveform generation. Yeah.
The waves are based on Verilog concepts of signals and force, or on Chisel things like bundles and cases and bundles?
So
if I had a vector of bundles, for example,
yeah,
would I see that like that in the waveform?
you would see it look. No, it would be kind of like this 0 and 1 thing is something where it was a vector before, and then it got split out into the 0th and 1th first component. Is that? Yeah. Like, so this thing was originally enabled, REN with a 0, like with 2 elements inside of it, and so they both get split out as a 0 and first. Okay. So back to so now we're going to talk about what if we want to use something, if we don't want to use RoC, but we still want to extend the ISA in some way, and we want to modify Rocketship to use our new extension. So basically that results in us having to modify a lot more stuff, and it's a lot more complicated, but it's probably still worth talking about because probably there's many of you who want to do that. So the 4 places you would have to deal with it would be inside of RISC-V opcodes is the first place, where that's basically where our encodings are defined. And then RISC-V GNU toolchain, which is obviously where you'd have to deal with the bin utils and the assembler stuff. And then the ISA sim, you'd want to, again, do a functional model of your instruction. And in Rocket, you'd have to do a lot of updates as well. So I'll quickly step through. So basically in RISC-V opcodes, this is a repository, and we have a makefile that generates all of these different header files that we need for all of the other places where the encoding comes into play, including basically the GNU toolchain, the simulator, the manual tables, and even in Chisel. And so you would basically add your instruction into a table like this, and you can read the formats pretty well defined in here. And then you would type make install, and it would generate the new instruction encodings for you. And then the next step for your non-RoC extension would be to go into the tool chain, and you want to look in basically your opcodes directory, and you see in here there are a bunch of, so here are like the RoC instructions, right? They're defined as, they're mnemonic, and then the different operands they take. And you'd have to figure out how to do that and add your thing here. And then if you rebuild the tool chain, your new instruction will be, you can assemble it. And the next step then would be to go into the ISA sim, and you see that all of the current instructions are defined in here, and you would basically, when you add it in the RISC-V opcodes directory, your mnemonic, you would need to fill in whatever header file with how you would fill in the header file with, basically a functional model of your instruction. And there's plenty of, as you saw, there's tons of instructions in the directory to figure out what you want to do. And so you'd also, in order to get it to integrate with Rocket, you'd have to modify that, but that's a significantly more complex operation, so I'm not going to go into detail into that, but during lab time, which is almost now, we can talk about it in person, and I'll be happy to try to work through your example. So the last few things is talking about Verilog generation and ASIC backends and FPGA backends and exactly how those can work. So as I was mentioning before, the vsim directory is where the build files are located for the Verilog stuff. And so if you type make in the vsim directory, it'll generate, and you can do the same thing here where you can use any config you would like, and it will generate the Verilog for you. I believe it's going to ask for VCS at the end, which we won't have, but we can just see what the generated source files are after that. Quick compilation process. But yeah, so basically this is going to generate, in the generated source folder, you now have your Verilog file, the .v file, as well as some of the different things that you're not used to. Maybe this is the exported parameters from your configuration file, and then you also have the thing that might actually be interesting is this is a configuration file for all of the memories that Chisel found in your design. And basically, because we know that we want to put these as SRAMs in our design, we leave them just as templates in the Verilog file. And we have a separate script, this VLSI memgen script that goes through and reads these parameters and calls, looks for the SRAM macros that we have and fits them into place. And so then that memgen script processes the Verilog and instantiates those things, and then that Verilog is ready to go off and be shipped to the CAD tools. And so in a similar manner, we have an fsim directory for FPGA Verilog generation. And here I won't go through the exercise of typing make, but basically you get these Verilog files again, and the same PRM file and the same conf file, but instead you would use the FPGA memgen, which is a similar thing that might be much simpler than your VLSI memgen, not having to worry about SRAM macros. But after you have that, then you copy these files into your FPGA subdirectory. So if you want to use your Z board, right, you go in here and then you just type, there's instructions, very detailed instructions in here about how to do it, but basically you just type make rocket, and then you type, make your boot.bin, and and it boots up Vivado and gives you a boot image ready to transfer over to FPGA. And that's all I have. So now I guess it's ready for lab time where we can all go around and help people.
No, I'm writing a Chisel program, and I'm compiling it for C++ simulation, and I want to plug in something that might go read a file or open a socket or something, right? Which is useful in test benches.
Right, yeah, so there's a standard way to call the simulation. There's a standard way to call the simulation. There's hooks, so you can write a little harness to drive it, and I think that's the way that it works for the rocket chip. You
Yeah.
know that they.
Yeah, let Yansub answer. He's got that.
Yeah, so I think I can help answer this one. The C++ test harness is actually, once you generate this Chisel module, it will have the IOs. So it's basically, you can read it every cycle. And you have, your test harness is calling the tick function every cycle. So once you call that, then you have all the IOs sitting, and then you are actually just, writing general C++ code to read them out. So like sockets and everything else, you can all write that in your test harness. And that's how we actually talk to the front-end server. It's not through a socket, but it's even another P thread running next to the actual simulation. And then it's doing user context switch between it. And then there's a front-end server running on another thread. That's actually really helpful to integrate things, as you said, with simulators, like your test harness test infrastructure running on your host machine. Oh, and actually the DRAM Sim 2 model is also running on another C++ part of the code.
So for the FPGA implementation, do you generate constraints?
Yeah, that's all kind of encapsulated inside of that FPGA repo. And you can see, if you look into that, there's a lot of instructions on how exactly that works. But yes.
Do you have a more sophisticated example of ROC interface? I was looking for something that the instruction just starts the coprocessor, and coprocessor starts fetching its own data and its own instructions, because the interface has the capability.
Yeah. So for the class, we don't have that example ready, but we have internal tools that we do that with.
But is there an example that I can take a look at?
Yansub, what do you? I mean, yes, it's Watcha, but
No, it's not part of the rocket chip. It's actually right now closed source, and kind of the main reason is because it's not really cleaned up. If you're really brave enough, I mean, we can work out some, some early alpha. I don't know. Yeah. We'll talk about it during the lab time.
Yeah, another thing with the vector unit, we are working on the vector ISA, a draft proposal for that, and I think we'd want to. The other reason not to release it yet is it's not going to be the same as the current hardware. So if we'd like to put the spec out with the vector unit implementing the spec we're putting as a proposal, and then they'll come out together, hopefully. Like I said, that's kind of a 3-4 month kind of time frame, I'm guessing. Yeah, basically, these usually the advances are driven by tape outs. Those are really hard deadlines that this chip has to have this thing on it, and that's when things get done. So,
I mean, so basically, Chisel is kind of the hardware description language, and so if you have a for loop, you're trying to create multiple separate things. Is the idea? You're like generating a set of things. If you have a for loop that creates a bunch of things, and so it would turn into multiple instantiations of whatever object you were making in the for loop, if I understand your question correctly.
I think the way to think about this is the Scala program in which you have Chisel is just a library in Scala. It creates a data structure which represents your circuit. That elaboration phase may include loops or whatever function calls, whatever, to build that data structure that represents your circuit. So at some point you finish the elaboration and you have basically a graph of components. We then take that graph of components and generate Verilog from it. So that elaboration phase decides how many pieces of stuff, different things you have. Like the for loop, for example, could be done during elaboration. I'm going to construct n instances of an adder or something and hook them all together. That then builds a graph, which is just a data structure in Scala. And then the backends take that data structure and spit out Verilog from them, or they take that data structure and spit out a bit accurate, cycle accurate C++ simulation. This is sort of standard. BlueSpec does exactly the same thing. It works the same way. So you have very important to distinguish this elaboration from the final output generation. And so one thing that's happening with Fertile is, we're sort of exposing that, as Fertile, we're exposing that internal format, and so allowing people to add new transformation and passes that you can first elaborate out a design, and then write transforms that take that graph and expand upon and do something else to generate a new instance of that or add things onto it. And then finally, you'll feed that thing into the back end, which will spit out the Verilog or the simulation of that elaborated and transformed RTL.
So how do you control that?
I mean, you're right. You have complete control. That You write programs that build that internal graph, then the backends will take it and spit out the Verilog from there. I mean, so you can literally, the basic Chisel primitives, every statement corresponds to somehow mutating and building a data structure in memory as a Scala data structure. So for example, when you write a statement, what you're doing is usually adding a component to that graph. And then when you do a wiring, you're sort of connecting two components in that graph. And so you're sort of manually, well, programmatically constructing this data structure. And the thing is, we sugar it up, so you think you're writing a hardware description, but what you're actually doing is manipulating this graph structure in memory. And then finally, the last part of Chisel is this library that takes that data structure and spits it out as Verilog or C++. So you have complete control over how that is built, and that's part of the power here, is that you can write arbitrary code to generate arbitrary lumps of hardware, and you have complete control of exactly what's in there. You can do it gate by gate if you want. But the other power is we can layer things on top. So the elaboration is done at a much higher level. You think you're writing, behavioral HLS kind of code, but it's actually just a sequence of transform all the way down to just snapping components into this data structure at the bottom. Okay, thanks, Colin.